All right, students. Now we will continue with the rest of the examples. And we've done part A and we've done part B. Now let's get down to parts C and D here. Find dx dt when theta is equal to pi over 6 and interpret the meaning of this equation. Okay, so let's make a quick note here on the side. I'll make it over here that x of theta is r cosine of theta. Okay. So we have to convert from r to x, and this will give us 3 minus 2 sine 2 theta times cosine theta. Okay. Now, in order to answer this question and find dx dt, we have to take 3t and plug it into both of these thetas. Okay? But we can also approach it another way, that x of t is really equal to x of theta of t. Therefore, the derivative of x with respect to t is equal to the derivative of x with respect to theta, so the derivative of the outside function, times the derivative of the inside function, or theta prime of t in this case. And then we can express this in a different notation. Dx dt is equal to dx d theta times d theta dt. Okay. And again, yes, nice mnemonic here. If you cross out the d theta, you end up with dx over dt. Okay. So now we want to find dx dt when theta is equal to pi over 6. Okay. So that means we need to figure out what's dx d theta at pi over 6 multiplied by d theta dt. Now remember from the original problem that theta is equal to 3t. Therefore, d theta dt is always equal to 3, so we can just multiply 3 right here. And then we could take pi over 6, substitute it into this formula, or this equation. We have to take the derivative of this, and then substitute pi over 6 into there, and then we'll be able to get our solution. So x prime of theta is equal to the derivative of the first. Since this is a product, we got to use the product rule. And that's going to give us negative 4 cosine 2 theta times the second part, which is cosine theta, plus the, I'm missing a parentheses here. That would help if I write this correctly. And then plus the derivative of the second, which is negative sine of theta, taking the derivative of cosine, times the first part, 3 minus 2 sine 2 theta. Okay. And then x prime of pi over 6. So taking pi over 6 and just plugging it into everything. So let's work out all of the fun trigonometric work here. We have, let's see, pi over, so negative 4 cosine of pi over 6 times 2 is pi over 3 times the cosine of pi over 6 minus the sine of pi over 6 times 3 minus 2 sine of 2 times pi over 6, or pi over 3. And then let's crunch out all of that arithmetic. So not arithmetic, but trigonometry. So after I evaluate everything, I get that. And then now we can do some simplifications. So the 4, the 1/2, and the 1/2 are all gone, and I get negative root 3 minus this 2 and that 1/2 are gone. So minus 3/2. No, I'm sorry, hold on a minute. Yeah, minus 3/2 plus root 3 over 2. So this is negative root 3 over negative root 3 and root 3 over 2. So that gives me negative root 3 over 2 minus 3. Root 3 minus 3 over 2. Okay. So just to get some sense of the number, we can take some estimation here. Well, actually, let's wait on the estimation. So now we can take this result and plug it in here. Negative root 3 minus 3 over 2 times 3. And now we can take the estimation. So I get an answer that, and just to be clear, this is dx dt when theta is equal to pi over 6 is approximately equal to negative 7.098. And more important even than the numerical answer is the interpretation. So this theta here, remember, is how far or how much the particle has rotated. So this means that when the particle has rotated pi over 6 radian, or 30 degrees, at that very moment, its horizontal position is changing at a rate of negative 7.098. Okay. So let's think about this again in context of our little graph here. So if I hit trace when theta is equal to pi over 6, okay. So right there, at that moment, the particle is moving left, so its position is changing, and the derivative with respect to t. So at that moment, it's moving to the left at a rate of 7.098 units of distance divided by seconds, since t here is measured in seconds. Okay. So from this graph alone, we really can't tell that. Your handy-dandy calculator only calculates derivatives with respect to x and with respect to theta. So we really have to do a little bit of extra work here in order to figure out how everything changes with time. All right, so now we can proceed to the last part here, which asks us a question about speed. So find the speed of the particle when time is equal to 4. So now we want to know what's happening when t is equal to 4. So just a quick conversion here. Remember that theta is equal to 3t. So if t is equal to 4, that means theta is equal to 12. Okay. So I'm just going to do this quick conversion so that if I need to plug theta in somewhere, I can do it relatively quickly. Now recall from our lesson on parametric equations that speed is equal to the square root of dx dt squared plus dy dt squared. Okay. Except now, instead of having an equation in terms of x and t, we have an equation in terms of r and theta, and of course we can convert it relatively quickly to x and t. But I'm going to expand on this a little bit and say that, well, what is dx dt equal to? Well, dx dt is really dx d theta times d theta dt. And similarly, dy dt is really dy d theta times d theta dt. Now, why bother doing this when, it seems like we've complicated things? But in this example, it's really nice, if you recall, that d theta dt happens to be a constant. So we get that this is really equal to 3. We can put a 3 here and then square it. So we get 9 dx d theta plus 9 dy d theta. Okay. Then we can factor out the 9 and then take it out of the square root, so we get 3 dx d theta. Oh, these should be squares still. I'm sorry. Made a mistake here. Dx d theta squared times dy d theta quantity squared. Okay. And if you notice here that this example, I haven't actually solved it or answered the question yet, but you could see here that if we were to back up into this step, we could factor out a d theta dt out of the square root entirely. So after we finish this example, maybe I'll go back to this and show you kind of a general process to it. But now let's go into this part and work on the whole issue of figuring out what is dx d theta, okay, and dy d theta. Now I've already figured out dx d theta from the previous problem. It's equal to this. Okay. And now we have to figure out dy d theta. And I'm sure you can do it, but for the sake of time and just solving this problem, I'm going to let my calculator and also show you how my calculator can work. Your calculator can work for you. Okay, so we know that x is equal to r cosine theta and y is equal to r sine theta. And I'm going to, for the purpose of this, just showing you a nice calculator trick as well, in addition to answering the question. So I'm going to change my mode here back into function mode, and then I'm going to go into y equals, and I've already typed this in. So if you don't remember, we hit vars, go down to polar, and pick R1, okay, and then cosine, and the theta button is alpha, and then the number 3. So that'll give us that result. So I have r cosine theta, r sine theta, and I'll get out of here. And some of you have nicer calculators than I do, so you'll be able to do this even more efficiently. So math and deriv, and we're taking the derivative of y1, because remember y1 is r cosine theta squared, okay, with respect to, we're not squaring that. We're going to take the derivative with respect to theta when theta is equal to 12, okay, squared, plus the derivative, and this time of y2, okay, because y2 is r sine theta with respect to theta at 12 squared. Okay. So that accomplishes this part right here in the square root. This should be a plus sign. What am I doing? This right here should be a plus sign. Okay, that plus, and that's a plus sign. So then we need to take the square root and then multiply it by 3. And so we get our final answer is that the speed is equal to 15.305. Okay. So at the moment in time when t is equal to 4, the speed of the object is moving at this pace. Okay. Now, there's other ways to do this, of course. You could have just made all the substitutions of wherever you see theta, plug 3t in there, and that would have worked just perfectly fine. This would also work perfectly fine as well. This video is getting a little bit long, so I'm going to end it here, and then I'll add another video where we talk briefly about this result here. There's a general rule that we can extract from this that isn't too difficult to do. In fact, if you're pretty sharp and you're in a good mood, you could figure this out for yourself. Thank you for watching, and have a wonderful day.